Hey, we've got Stephen Austell on board. Good deal. Tuesday, December 1st, Physics 2. And Stephen's here with us. And Phoebe's here with us.
Yes, I'm driving. I'm sorry.
Yeah, you be careful. And I was looking at the homework there. It looks like you have one more homework assignment. It's homework number 16. And it's problem 1533 in your book. I'm curious to see what that is. Okay, it's an RLC circuit. Let's do a similar one. We're having a semester review tonight. Your final will be available a week from tonight, or a week from today in the morning, and then you can turn it in. The due date is the 11th. See, today's the 1st, so your final will be available a week from today. And so we're going to spend our time tonight going over some stuff I hope that we understand.
Every one of you that made it this far in the video. Just so we can know your name, please write RIN in the comments, which stands for Reality is Negotiable.
I don't know whose voice that is. Do you guys have any idea? Somebody has on a recording or something. It's not me. Okay, well, let's get started. I'm going to give you a problem here to work. And these are just practice problems. This is an AC circuit. This is 110 volts AC, 60 hertz. And we've got a light bulb that's got printed on it 40 watts. I'm going to put that in quotes. And we have a capacitor that's 15 microfarads. This is an AC circuit, as you can see. That's the symbol for an AC circuit. Okay, well, the first thing we've got to do is realize that this light bulb is just a resistor. So we could make an equivalent circuit like this. (110 volts, AC, 60 hertz. But we need to find, we know what the capacitor is, it's 15 microfarads, but we need to find what the resistance is of that 40-watt bulb. Now I'm going to shut up for a minute, and I want to see if you can do that. See if you can find what the resistance is of that 40-watt bulb, and then we'll do it together. You have about a minute. See what you can do. If you tuned in late, Right now, we're finding the resistance of this 40-watt light bulb. Let's see if anybody else has showed up. Yeah, we got Zach. Zach's with us. Stephen and Phoebe. We've got a class. It's small, but it's okay. And we're finding that resistance there of that 40-watt bulb. Well, let me see if my friend Zach. Zach, do you know what the resistance is of that 40-watt bulb?
No, I'm still setting up. No, I'm still setting up. Can you hear me?
Oh, yeah, I can hear you. You're still setting it up? We'll give you a little more time. Give you guys a little more time.
No, I'm setting up, period. Yeah, no, I'm setting my stuff up. But yeah, go ahead.
Well, what about my friend Stephen? Stephen, do you know what the resistance is on that 40-watt light bulb?
I'm trying to remember which formula.
Yeah. Well, maybe it's good to have a review once in a while of stuff that we're supposed to know. Here, let me help you guys. I'll give you a little help here. There's a lovely formula that goes like this. I know you've seen that formula before. There's actually 3 formulas for power. But on this one here, we're given the power, it's 40 watts. And if you have a 110 volt source, we know the voltage, so you can find the resistance. Now find it. Did you get?
302.5?
Yeah, that's what I got. I got a resistance of that bulb, 302.5. Here, let's put it right here. That was a little confusing, but I think we're okay. We've done this before. So now we know what it is. It's really a resistor is all it is. We don't need this circuit here anymore. Now we know the frequency is 60 hertz. But we're going to need the angular velocity. I want you to find the angular velocity. See, that's what this represents here. This represents a sinusoidal voltage that can be expressed as an angular velocity. And the angular velocity is equal to 2 pi f. So what is the angular velocity?
377.
You got it. It's equal to 377 radians per second. Now, radians are dimensionless, but I'll go ahead and write them out. They're not really a unit. Okay, so you know what we have? We have a AC circuit, and we need to draw the impedance diagram. I'm going to shut up again, and I want you to draw the impedance diagram. Now to do it, we're going to need something. We're going to need what they call the capacitive reactance. Do you remember that? That's 1 over omega C. I want you to find that, capacitive reactance, and then I want you to draw the impedance diagram. Again, I'll let you work for a minute. I wonder if anybody else is going to show up tonight. Let me see here. Nope, it's just the los tres amigos, amigas, or whatever. We only got 3 of us, but that's all right. Well, I did that, and I got an answer. I got 177 ohms. If that's what you got, say uh-huh.
Yeah.
Yeah, there we go. So we know this, it's 177 ohms. Now we're going to draw the impedance diagram. Do you remember how to do that? You draw the 177 going down. There is no XL. There is no inductive reactance because there's no inductor. But you do have a 302.5. That's pretty long. It's way the heck out here. That's your resistance. It's 302.5. And this is 177. And now we can get the impedance. See, the impedance goes from here to here. I want you to find the impedance, and I want you to find this phase angle phi. I'll shut up and I'll let you find the impedance. See, this is called the impedance diagram. Find the impedance, find the phase angle. Go for it. Stephen, do you have that impedance yet? Earth calling Stephen. Come in, Stephen.
Yeah, I'm here. Sorry.
Yeah, that's okay. Take your time. Have you got that impedance for us yet?
No.
Well, keep working. We'll get it. How about my friend Phoebe? Are you still driving, Phoebe?
Yes, I'm still driving.
Oh, you be careful. You be careful. I was out driving here a couple of hours ago and the traffic was really terrible. Just terrible. Well, I did this and I came up with an impedance of 350 ohms. You have to square that, take the square root.
I got that same thing.
Yeah, there you go. Good going. Proud of you. Okay, now we're going to get the current. Here goes. The current is going to be 110 volts. Now, you got to understand that's a RMS. When they say 110, that's RMS. And so this current is going to be RMS. And it's going to be 110 divided by your impedance, which is 350.4 ohms. Go ahead and get your current. And then when you get your current, I want you to find the volts. I want you to find the volts here on this resistor and the volts here on this capacitor. I'll shut up. You find the current and then find the volts on those two. Well, I got a current of 0.314 amperes, about a third of an amp.
Yeah.
With that, you should be able to get the two voltages. What'd you get for this voltage on this resistor, Zach?
94.98.
Yeah, that's what I got. I just rounded it off to 95 volts. And Zach, what'd you get for the voltage on the capacitor?
55.58.
That's what I got. I got 55.6 volts on the capacitor. Now let's figure the power in this circuit. Just need a little room here. If you watch the YouTube video, that'll be on there, but all that is, it should be on your Blackboard. All that information should be on Blackboard. So we're going to get the power now. Now there's an equation for the power of this circuit that goes like this. Hey, did we ever get this angle? No, we never got the angle. We're going to have to stop. You can't use that equation without that angle. So we're going to get that angle. Here goes. I'm going to find what it is.
I got 30.33.
That's what I got. Good going. It's 30.3 degrees. All right. You say it's 30.33. Let me double check you here just a minute. And not that I don't trust you. Yeah. Well, I'm getting 30.31. 30.3. Okay, here we go. We're going to find the power in this circuit. Now, these are all RMS values. They have to be RMS or this thing doesn't work. Well, the RMS current, we figured it out. It's 0.314 amps. And the RMS voltage is 110 volts. And the angle, the phase angle is 30 point. Now, actually, it's a minus 30. See, it's below the axis. It's a minus 30, but The cosine of a minus 30 is the same as the cosine of a plus 30, so it doesn't really matter. Okay, plug that in and let's get our power. Here we go. Well, I got the power. Yeah, I came out with 29.8 watts. Do you agree with that?
Yeah.
Yeah. Okay. Now there's another way to get this power. You got to understand something. This is average power. The power actually fluctuates because we have a sinusoidal voltage. And so we have an instantaneous power that's changing all the time. But the average power is 29.8 watts. And this resistor is the one that's using that 29.8 watts. The capacitor doesn't use any power. It stores energy and gives it back. Stores energy and gives it back 60 times a second. The average power of a capacitor is 0. So you can get the average power of this circuit. There's a couple of ways. One way is just to go I squared R. Now it has to be RMS.
You said the power of what is 0?
The power of the capacitor is 0. It's not using any power at all. Average power.
Okay, thanks.
Yeah, it's using power, but it's storing it up and then it's giving it back, storing it up, giving it back 60 times a second. On average, it's 0. But you can get the power of the resistor. Well, it's really a light bulb. And it's bright and it's hot. And you put your hand on it, it's kind of hot. See, there's energy there that's going out, warming up the environment. And you can find the power by taking the current, which is 0.314 amps, squaring it, times the resistance, 302. Go ahead and do that for me. Do the I squared R and tell me what you get for the power of the resistor. Go ahead.
I got 29.8.
Well, how about that? You get 29.8 watts. The resistor is using up all the power. The source is providing the power, and the resistor is using the power. Now you can get the power of the source. Let me make some room here someplace.
Are the inducers the same? Do the inducers work the same?
Yes. Inductors,
Inductors, yeah.
they don't use any average power either. They store energy in their magnetic fields and they give it back. Store it, give it back 60 times a second. Good, that's an intelligent question. Now one last thing here and we'll move on to some more fun things. The power provided, the average power provided by the source, we'll put source right here, that's equal to the RMS current times the RMS voltage. Well, let's try that and see what happens. Well, the RMS current is 0.314 amperes. And the RMS voltage is 110. It's 110 volts. Multiply that and tell me what you get.
Yeah, 30.
34.54.
Yeah.
Okay, here's where I've goofed up. I forgot the cosine of 30.31. We've already done that. Subtract everything I just told you there on that last bit. I forgot the cosine. We did that right here. See it? That is the power that's being supplied. There it is. It's 29.8. Okay, well that's enough of that one. Let's move on to something else. Any questions on that? All right. Well, here we go. We're going to try an RC circuit. I'm going to erase all this unless you have a question. Okay. Now that was an AC circuit. Now this is going to be a DC circuit. What we just did was an AC circuit, but now we're going to do a DC circuit. Okay, here goes. This thing doesn't write very good, doggone it. Now we got a battery here. Let's say this is a 6-volt battery. We have some of those in the lab. And we have a switch here. And we're going to throw that switch. And this resistor is 2 kilo ohms. And the capacitor is 8 microfarads. I think we've got some capacitors of that size in the lab and some resistors of 2 kilo ohm resistors. We could make this circuit in the lab very easily. Now the first thing I want you to find is the time constant. They call this the RC time constant. That's the name of it. See if you can find it. I'll give you a minute. Go for it. Find the RC time constant. They call this the time constant. Find it. Well, let's pick on Stephen. Maybe Stephen's got it. Hey, Stephen, do you have that time constant for us? Earth calling. Yeah, there
I've
you
got a
go.
whole bunch of decimals. I forgot to change my calculator to scientific.
Yeah,
Uh,
get it on scientific. That's a good idea. Yeah, we don't want to have it on the fixed point, I think they call it. Because in fixed point,
I've got 0.16 to the -9.
okay, now the 1.6 is right. But the -9 is not right. Here, let me write it out for you. That's a 2 kilo ohms. You know what that is? That's 2 times 10 to the third. And that's 8.
I put negative third.
You know what? You just got yourself a thank you point. I was wrong. It's negative third. Now that's 8 microfarads. That's times 10 to the minus 6 farads. Well, maybe you were right. Now, what did you say it was? 2? You know what, Stephen? I think you were right, and I was wrong. I think you were right. It's 16. What would that be? Would that be nano?
I got 16 milliseconds though. I mean, yeah, I did.
Okay, now just a minute now.
I got 0.016
Oh,
seconds.
wait a minute. Auga. Kilo is +3. That there's a +3. Hey, you don't get a thank you point for that. That's a +3.
Oh, I said I did the negative 3. That's where I screwed up at.
Okay. It's a +3. We got it right now, though. It's 16 milliseconds. Is everybody happy now? I love arguments with my students, but I think we got it right now. Is that what you guys have? 16 milliseconds?
Yeah, that's what I have.
Yep,
Yeah, I'm happy.
I got that now.
That's the time constant, 16 milliseconds. Okay, now here's what I want you to find. I want you to find the current after, I don't know, maybe, how about after 8 milliseconds. Find the current. See, when you throw that switch, you all know what's going to happen. There's going to be some current, and you're going to start filling up this capacitor. And I want you to find the current after 8 milliseconds. I'll be quiet, and I'll let you work for a minute. We've actually done this in lab. We've done this 2 different times in lab.